Okay, in this video, I want to talk about expand on my discussion in regards to tectonic plate movement. So, as it turns out, convection currents and gravity may actually be involved in the movement of plates. Okay, these two things. There's another theory of tectonic plate movement. I'll talk about the first one in terms of convection currents. The second one I want to talk about now is gravity. Okay, so in two different ways, here's how gravity can actually make them move. One of them is called the slab pull theory. Here, gravity basically pulls heavy and dense plate. So it starts off by pulling a heavy and dense plate downwards. Okay, and the subduction zone where the plates meet then pulls plate into the trench. The trench is like a gap, a hole in the ground, and away from ocean ridges. Okay, now I should also mention the plates at the subduction zones. Okay, the plates here are denser, are heavier than those near the mid ridges. The ridges, remember, is when they're separating out. Okay, there's obviously not many plates here, but there's going to be some plates here. Okay, overlapping. Okay, as you know, gravity is a force that acts between two objects. Okay, and the heavier you are, the greater the force of gravity. So obviously, heavier implies more gravity. So think of a trampoline, and think of placing a massive bowling ball in the trampoline. What does the bowling ball do? It basically causes a big dent. If you get a tennis ball instead of a bowling ball, it doesn't make a massive dent, right? Why? Because the bigger you are, the heavier, the fatter, the stronger the force of gravity. Same thing here. This is called the slab pull. The slab is pulled downwards due to gravity. That's number one. Number two, the ridge push. Okay. Now, since the new ocean crust is forming at the ridge is above the rest of the Earth, gravity pulls the new crust downwards. Okay. So since new ocean crust forming at ridge is above rest of the Earth, gravity pulls new crust downwards. Okay, this is push on the older crust below it and to the sides. That will make plates move. Okay, so let me just draw a diagram. So the ridge, as you know, is formed when they're moving apart. Okay, so you get new crust coming out here from the ground, new crust forming. Now, since it's above the rest of the Earth, okay, this basically comes up, yeah, as these move apart. Gravity pulls a new crust. It then compresses it downwards. Okay, so initially it comes up, but then gravity pushes it downwards. As you know, gravity is a force pushing everything downwards towards the Earth, and that's how it works. Okay, so initially it comes up between the two, and then gravity comes along and squashes it down. Okay, they're the two theories involving gravity. Now, let me now talk about continental drift. Okay. Basically, Alfred Wegener was a German scientist, and his theory, Alfred Wegener, so Wegener's theory of continents being once together is called continental drift. Okay, and this supercontinent, you should learn this word. Should be useful. The supercontinent is actually called Pangaea or Pangaea. I have no idea how it's pronounced. Doesn't really matter. It's just a word. Okay, Pangaea. Now, here's the evidence that Wegener used to support his idea. Here's the first piece of evidence. Okay, the continents seem to fit together like a jigsaw puzzle. Okay, they fit together like a jigsaw puzzle. And when you go back in time, the continents all fit together to form Pangaea. Okay, that's number one. Number two is fossils. Now, fossils of the same prehistoric species, were found on continents a very long way apart. Okay, and as they shifted, they took the fossils with them. So these two are pieces of evidence regarding continental drift theory by Wegener. Okay, moving on. Now, Wegener basically rearranged the continents, as I mentioned. He joined them up so they can, so the distribution of fossils matched up across the continents. So if I was to draw this in a terrible way, India, Australia. Okay, so here's Australia, here's Oz, here's Antarctica, here's India, here's Africa, and here's South America. And as you can see, they sort of fit together. And where these lines I'm drawing are where the fossils match up. They're identical, okay? Fossils here as well. Here, India, across Antarctica, and then across Australia. Okay, these all match up. That's what we were saying, and this is Pangaea, when they were joined together. It was the original landmass of the Earth. Okay, and it gradually broke apart into two. So gradually broke apart into two major landmasses. And you should commit these to memory, called Laurentia in the north. Okay, this is the north one, and Gondwana in the south. Okay, so two massive ones, Laurentia, Gondwana in the south. Okay, and Australia was part of Gondwana, actually. Okay, so actually they weren't all connected together. They were mainly, okay, there was massive pieces and there were smaller pieces. Okay, that's how it looked like. That was Pangaea. Then it became Laurentia and Gondwana. Okay, Gondwana consisted of Australia, Antarctica, South America, Africa, and India. Okay. And now some of the early ideas on the theory of continental drift. Okay, the early ideas were very limited in terms of understanding because scientists didn't have really technical tools back then, machines and stuff. And at the time, actually, few scientists agreed with Wegener's theory. Okay, because there was actually no way that they could figure out what was actually making the tectonic plates move, the continents move, right? An Englishman actually named Francis Bacon, Englishman named Francis Bacon in 1620, in the 1600s. Okay, he noticed that the eastern coast of America, okay, fit the coasts of Africa and Europe like jigsaw puzzles. Okay, and they were once joined together. That's what he thought. They were once joined together. That's an early theory of continental drift.